electromagnetic gyroscope. Background of the invention. This invention relates to inertial angular rate sensors and in particular to electromagnetic gyroscopes. Gyroscopes provide a measure of an angular rate, velocities and differential or integral functions of velocity impressed upon the gyroscope by producing a signal representative of the torques experienced by the instrument at any particular time. Typical prior art gyroscopes make use of rotating elements suspended by complex gimbal assemblies. The inertial torques impressed upon these instruments typically are measured by rebalance feedback loops. These prior art devices suffer from the number of moving parts involved, the delicate nature of the structures, and difficulty in manufacturing. There exists a need for better gyroscopes suitable for robust service in adverse environments. In particular, reliable gyroscopes which can fit into small volumes and perform without moving parts would satisfy a variety of long-felt needs in aeronautic and related industries. The electromagnetic gyroscope of the present invention is a device for measuring an inertial angular rate based on the inertial properties of an electromagnetic field. The present invention contains no moving parts, but produces an output voltage when it rotates relative to inertial space. The operation of the present invention is based upon the principle that a conductive path traversing a magnetic field will generate an electric potential difference between 2 points on the path when the path rotates about an axis relative to the inertial reference frame. To sense rotation about the axis, the 2 points on the path need only define a capacitance sufficient to drive a sensing circuit. Conceptually, the principle of operation can be understood by considering a permanent magnet surrounded by 2 concentric metal cylinders coaxial with the magnetic field axis, and where the cylinders are connected through a voltmeter by a radially extending wire which passes through the axial field. Upon rotation of the cylinders together about their common axis, electrons in the wire experience a radial force proportional to the product of the magnetic field and the angular velocity. In response to that force, a net flow of electrons takes place from one cylinder to the other, resulting in a potential difference between the cylinders. Since rotating the magnet about its axis does not change the magnetic field, the potential difference or voltage between the cylinders resulting from the electron flow is generated solely by the inertial rotation of the cylinders and wire in the magnetic field, and not as a result of any relative motion of the magnet and cylinders. Hence, the voltage between the cylinders, or the charge on the cylinders, is a direct measure of the inertial angular velocity of the cylinders. In order to measure the induced voltage, the radial wire need not be connected directly to the outer plate, but instead can be connected to one terminal of a voltmeter. The other terminal of the voltmeter is connected by a wire to the outer cylinder. For the case of an infinite input impedance voltmeter, the voltage reading is directly related to the inertial angular rate of the assembly. Since practical voltage measuring devices will have a finite impedance, preferred embodiments of the electromagnetic gyroscope will, in most instances, employ an electromagnet excited by an alternating current waveform rather than a permanent magnet to accurately measure angular velocities. In one simple embodiment, the gyroscope consists basically of an electromagnet including a cylindrical coil extending about an axis of symmetry and an associated power supply, housed in a grounded cylindrical metal case which extends along the coil axis. In this configuration, the grounded case acts as an outer cylindrical electrode, and a second casing surrounding the coil acts as an inner cylindrical electrode. The electromagnet produces a magnetic field having an axial component passing between the outer electrode and the inner electrode, and having an oppositely directed axial component within the coil. A wire is connected to the inner electrode and passes radially through the field between the electrodes and then out a hole in the outer electrode to one terminal of a voltage sensor. The other terminal of the sensor is connected to the box. In operation, as this assembly is rotated about the axis of symmetry, electrons in the radially extending part of the wire, which intercepts the magnetic field, experience a magnetic force which tends to draw charge from the coil shield through the voltmeter to the outer electrode. The open circuit voltage is given approximately by V equals F of across R times BDR, where V is the line integral of the induced electric field intensity, U cross B, along the radially extending part of the wire RA is the radius of the inner electrode having an oppositely directed axial component within the coil. RB is the radius of the outer electrode, omega is the vector angular having an oppositely directed axial component within the coil.
You ready to